So today we're going to be talking about segmentation in healthcare. My name is ChiChi. I recently graduated from Berkeley. I did my undergraduate as well as my master's there in bioengineering, and I'm currently about to start my PhD at Columbia University. So today I'm going to give you a little quick overview on what we'll be talking about today. So the first part would be, what is image segmentation? I'm going to give you guys a very quick review on image segmentation. If you guys want a more in-depth, understanding of what image segmentation is, please feel free to look at a previous video that was posted by Meta as well. It is a video series that talks not only about image segmentation, but also registration, classification, and prognosis. And I think it would be super beneficial for you guys if you guys haven't come across image segmentation at all before. The second part of this, we'll talk about the different challenges that are currently being faced in image segmentation. So these challenges are not only in clinical settings, but also in a lot of the academic research that are being done in image segmentation. And as we're moving on to the second part of this, we're going to be talking more about solutions that actually address the challenges that were mentioned previously. And some of these would be the different loss functions that may be currently used to address the challenges that we talked about before. And we're going to wrap this entire thing up with a little bit of an explanation, about federated learning. So federated learning is specifically a solution that actually addresses data privacy issues. So we're going to give you a quick introduction on what specifically is federated learning, as well as how can federated learning bypass this data privacy issue that we're currently facing in medicine. So we're going to start off with specifically what is segmentation. A very quick review. So let's look at this image. Look at the image on the left side. Immediately as humans, what we actually first see is we see cars, right? We also see the crosswalk. We see the roads. We see some people. We see houses in the background. These are things that our brain kind of intuitively identifies and notices in this image, objects that are there. However, from a computer's point of view, they do the exact same thing. But we're able as humans to identify a car because we're able to see the taillights, we're able to see the tires, we're able to see the windows as well as the structure of the object. That gives us a kind of intuitive understanding that this is definitely a car. So from a computer's perspective, what they actually do is they don't need to know about all this stuff. Just like how, as we have identified that this is a car, we don't need to talk about the different details of the car. We just need to identify and categorize that as a car, the same way that this computer is doing in this image on the right side. They're giving it a specific color to kind of say that this is the outline of the car. The yellow things that you see at the front are objects that are the crosswalk. The red stuff, all that stuff in the background are all houses. You don't need to identify which building is what. All you need to know is that these are all buildings. So image segmentation, you can think of, is splitting up these different objects or segmenting these different objects in an image to give this image an entire, in a sense, a much easier and more efficient way of processing this image immediately. So as you can see the difference from this original image versus the segmented image, it's a lot clearer specifically what we're looking at. You see the people, you see that there are different kinds of objects, maybe 4 or 5 different main objects that you actually see in this image that we really truly care about. So image segmentation, I'd like to say in a nutshell, is our way of partitioning this image into something and giving it labels to kind of give this image a lot more of a meaning to it. So if we had to really put that into a summary or into words, it is the partitioning of images into meaningful segments. So if we applied that to medicine, it basically means that we are identifying pixels of organs or of tissues or other biologically relevant structures so that doctors, as they're looking over it, they're looking at the things that they may care about. For example, from a brain's point of view, if you're looking at a tumor, you're also identifying the pixels of the tumors that allow a doctor or radiologist or physician to really quickly and efficiently look and see what they're actually identifying to make a better process of diagnosis, to speed up that process as well, making it more efficient so that you don't have all these other structures that may potentially be in their way. And we'll see how in this next slide. So if you see, these are the images at the top, what doctors, radiologists, physicians, oncologists usually look at, right? And to them, obviously, through years and years of experience, this becomes intuitive. However, what actually enables us to be able to clean this image up is image segmentation, as you can see in the bottom. You're outlining all these different tumors, as we saw previously, kind of like in the same situation as the cars. We don't need to look at the details of this tumor, just more or less specifically the depth, the outline, what it actually looks like, where it actually exists. So that, for example, if we were to go into surgery, you know that there's this little bit here that you can't really cut off because it's not a very quick or a very like nice and smooth kind of curvature, but instead you have all these like different small ridges to it. That is super important when it comes to surgery. So from a doctor's perspective, you can look at this and be like, well, there's all this that I need to be careful of, or there's all this that I need to be careful of when it comes to treatment. It actually makes their lives a lot more efficient and a lot easier. And it makes it a lot better when it comes to segmenting things. It's a lot cleaner in my perspective. So let's talk about these different challenges that we may be encountering with image segmentation. We've talked about how great it is, how it's beneficial to this medical field. But what are the challenges that are being currently faced? So the very first thing that you'll know in research, as you'll see a lot in papers, as well as what researchers and doctors may tell you, is an issue of class imbalance. So we'll talk about how so in more detail later by giving you an actual a formal definition. But in a nutshell, I'd like to say class imbalance is a systemic limitation. It is very much, if you think about it, if I had to quickly summarize, it's if you had two things in this image, for example, non-tumor and tumor, the space that you have for non-tumors is going to be a lot more than the space that you have for tumors. Or the data points that you have for non-tumors is going to be a lot more than the data points that you have for tumors. This, as a result, creates some sort of class imbalance because you have two classes, tumor and non-tumors. These are two classes and there's an imbalance because of the numbers that you actually have for each of them. And as a computer, you're going through all this data. You can only learn tumors from that small set of data, and that becomes a systemic limitation, right? Because it's a technological informatic kind of issue where it's like you don't have enough information to give you enough confidence to be able to predict something. And as a result, that may affect your accuracy. And we'll see that how in the next slides. And so the second challenge that we often see in image segmentation is imbalanced data. So what I mean by imbalanced data is think about cups in general. We tend to notice cups, or the very first kinds were like the mugs, where you actually have the ears, as well as a round part, and you kind of hold it to drink your tea, right? So this is our kind of interpretation of a mug, or of cups in general. However, people who may have, this is a general kind of observation. However, there are maybe a set of people who may have noticed these venti-sized cups that you see from Starbucks. Those actually don't have the mugs with the ears on the side. There's a possibility that because there's such a small subset of people who've actually seen these and identified these as cups, people who have never seen it might say that, hey, I don't think this is a cup. It might be a trash can. It might be some other kind of holder. And so naturally speaking, what I mean by imbalanced data sets is that there are different characteristics or different descriptions that we can give to different objects, such as the fact that we see different kinds of chairs. Some may be 4 wheels, some may be 5 wheels. But these different characteristics that are given to these chairs, at the end of the day, they're still categorized as chairs. So same thing as tumor. We know that medicine in general is very uncertain. The most uncertainty actually exists in medicine. And that comes naturally with tumors, right? Tumors may have different shapes, different sizes, different kind of surfaces. All of these things can affect how a tumor looks. And sometimes you may train it on bigger data sets, train models on bigger data sets versus training them on smaller data sets. And a challenge that we have also personally seen ourselves as we're doing research is that as we're training them on bigger data sets, or like, for example, data sets with bigger tumors, they tend to miss these smaller tumors a lot more because what this model has learned is that this size that is a lot bigger is what a tumor should look like, instead of the small things which they may completely just miss out or kind of interpret that as some sort of background noise. And so this imbalance in data in terms of the models that we're actually training it on, we know at the end of the day, as always, we like to say, models are only as good at predicting as the data set that you actually feed it. So if you're mostly only feeding big tumors, or if you're mostly only feeding small tumors, their prediction is only going to be as good as that data set that you're giving it. And that's one of the biggest challenges, because there isn't a singular model that we've been able to find that actually works 100% on all kinds of tumors, because tumors are actually so different in terms of the way that they grow and then the way that they are presented. It actually creates that difference that makes it a lot harder for models to really accurately predict it. The third thing is the diverse data sets. So this is an issue that I'd like to say in a more clinical setting. So from a researcher's point of view, if we're trying to offer this model or this algorithm to clinicians or to hospitals in general, we want to be able to validate it. Just because we've trained this model on our hospital data set and we've gotten a very high accuracy rate, we have personally noticed from research that this is not necessarily going to be true if we put this in a different data set. And so what we mean by is, for example, if I train in a hospital A and I got a 96% accuracy rate, this accuracy rate may drop if I train it on hospital B data set. And so these differences, which may result in demographics, which can result in lifestyles that may affect the different kinds of tumors that we're being trained on, these different kinds of models may not work as well on these different diverse data sets. And as a result, we need some sort of way, because we can't access all this data all at once due to like a lot of these different regulations, there isn't an actual way for us to be able to validate the models that we're using. So the one thing that we'd like to say is that models, as I said before, models are only so good at predicting depending on the amount of data set and the type of data set that you're feeding it. And so the more data set you're able to feed it, the more you're able to train it, and we'll see how federated learning is actually the best solution to be able to get to where we want to get to in a few years. So first of all, let's talk about class imbalance. So class imbalance, I'd like to define it as the total number of a class of data points, which is positive data points, is far less than the total number of another class of data points, which might be negative. So in the case of tumors, it might just be non-tumors is negative and tumors is positive. So let's look at this image right here of this woman. It's split up into the person in the front. You see in the back, you see the plants, you see the trees, and you see the ground in the background, right? You also see the grass and some sort of like, some sort of thing at the in the back, like a building. So all these different kinds of objects, as we saw earlier with the car situation, is given a certain number as a mask. And so, for example, the lady in front might be 1. And let's just say that everything else in the background is considered a 0. What I mean by class imbalance is if you add up all the 1s and add up all the 0s in the background, what you're going to notice is that there isn't going to be a 50-50% split between these 0s and 1s. There's definitely going to be more 0s because there's more background at the end of the day in this image versus the person that you see in front. Or there's going to be more information on non-person versus person in this image. And this class imbalance can give you some decrease in your model's accuracy, because at the end of the day, you have more data points on things that are not a person, right? So it's a lot easier for you to learn what it means to identify an object that isn't a person, versus if you only had 10 data points on a person, you're like, okay, well, I can only work off of these 10 data points. So you have less confidence to be like, this is definitely the person that I was looking at before. And so class imbalance can actually also give you a false sense of accuracy, as we'll see in an example later. So if we had to apply class imbalance to medical imaging, as we can see here, this is the image that doctors usually look at, and we have this mask that is created out of it, right? And we can clearly see in these two images that there is a class imbalance that exists, because what you see in the front, or what you see as the white spot, is the tumor. That we can label as all 1s versus all the 0s of the black background in the background. And so the number of data points that you have on non-tumors is a lot more than tumors. And so as a result, it is a lot easier for this algorithm potentially to learn what a non-tumor looks like than what a tumor actually looks like. So let's give this an example to make this a little bit easier to understand, hopefully. Let's just say that we had 10,000 data points that told us what a non-tumor looked like, and 10 data points that told us what a tumor looked like. If we had to do this mathematically speaking, let's start off with the right side, or let's start off with the left side, sorry. If we had 2 models actually to predict this, And the first model actually predicted 7 wrong. So out of the 10 tumors, they assumed that 7 were actually non-tumors. They predicted 7 wrong out of the 10, right? And for model 2, they actually only predicted 2 wrong. So of the 10 tumors, they only predicted 2 as non-tumors. Just immediately, intuitively speaking, we know that model 2 is definitely better than model 1 at predicting the number of tumors or predicting what a tumor actually looks like, right? But if we looked at the math on the left side, if we only looked at the number of right predictions, we can see that the error rate for model 1 is a lot lower than model 2. So this gives us a false sense of accuracy in the way that we're actually looking at this class imbalance. Versus, for example, if we look at this other side of looking of interpreting this information. If we looked at false positive, true positive, and false negative rates, what we'll actually notice is that our false negative rate for a model 2 is a lot lower because of all the actual truly positives, or of all the patients with tumors, they were only predicting 2 wrong, which gives us a 20% incorrect rate, which obviously is a lot lower than our model 1, which actually aligns with our original hypotheses. So this gives us a sense of how class imbalance can actually affect the way that we train our models and how accurate our models can be. So the second issue that we talked about was imbalanced data. And as I mentioned before, data, like a lot of other objects, naturally speaking, have different ways of being characterized or described. And as we can see here in this image, there are 2 different kinds of tumors, right? So one of them is kind of long and lopsided with different shapes that you never really would have assumed would be a tumor shape. This is probably a more abnormal tumor shape. So you can know that's growing faster longitudinally. Whereas the other one you can see is kind of more circular. So if we train the model on the tumor that you see on the right side that is more circular, maybe this model is going to identify tumors more or less as ones that look like that, rather than the ones that you actually see on the left side, which look a little bit more abnormal. And so these differences in these tumor size and these tumor textures, as well as location, as you can see down here, patient 1, patient 2, patient 3, and patient 4, they have different kinds of brain metastases, right? Patient 3 has less tumors, as you can see in these images, but they tend to be larger. Whereas patient 4 and patient 2 actually has a lot more tumors, but they're a lot smaller. So these differences in the way that tumors can grow, their sizes, textures, and tumor location greatly affect the way that our model is being trained. Because a model that might be trained on patient 3 is going to give us a different accuracy if it's trained on patient 4. Because it is very likely that it may treat all these smaller, very, very small dots that you actually see in these images as just background noise, or things that they may potentially as just like structures that they see, rather than actual small tumors. So as a result, this imbalanced data can decrease a model's accuracy. So the third thing we talked about was diverse data sets. So this is different for different hospitals, different institutions, different cases. So different patients may have different kinds of tumors, right, as we were talking about before. And there's a very, very strong need for diverse data sets when we're trying to validate our model. Because at the end of the day, you don't want to use one specific model on the previous data that you're looking at. What you want to do is to constantly learn something new from across different people, across different countries, in order for you to actually gauge a very, very good understanding of what tumors can look like. Because as we kind of start changing, as we start evolving, these tumors also start evolving. So the best case scenario is learning how all these different tumors can look like, or how tumors can be characterized in the millions of ways that they can actually be described as. And collecting all this data set is going to give our model a better way, or a more accurate way of predicting whether or not we actually see a tumor in these images or not. So one thing that's super important is that different data sets can decrease a model's accuracy. And we're hoping that we're able to achieve this through federated learning, because gaining access to all these different kinds of data sets across hospitals and institutions is very limited. And this limitation is mostly due to all these regulations that we kind of encounter in healthcare. It's one of the most restricted industries, and it is for a reason. You don't want someone that you don't know accessing a lot of these personal data that you may have on your health issues. And so the best way to be able to access all this is what we called federated learning. And we'll go into a little bit about that later. First, let's talk about loss functions. So as I said, for the loss functions, we're only going to talk about the general 3 that I think we encounter the most. And the reason for this is because I wanted to tell or show you guys how there are different kinds of loss functions that are currently, I guess, being kind of designed to be able to address a lot of these challenges and issues that we are facing, as I mentioned before. There are a lot more different loss functions that are coming up nowadays to address more of these issues, but these are mostly like the 3 different ones that I'd be introducing today that you would be encountering the most. So the first one is dice coefficient loss. This is a measure of the overlap of the predicted mask and the ground truth. So as you can see in this image here, A probably is the most overlap, right? You can think of the gray or like the pinkish color as the actual ground truth, and the actual blue as the actual, the blue is the actual ground truth and the pink as the predicted mask or the segmented mask. And so these are, the overlap between these 2 is going to basically give you that dice coefficient loss. So the more overlap you have, obviously, means that the higher your dice coefficient. So this is one of the most common way of actually predicting our losses. So our focal Tversky loss, as you can see, is that for the losses, or for focuses on hard cases, it allows us to focus on hard cases with low probabilities. And the reason for that is because this is actually, the Tversky index is actually built off of the dice coefficient loss as we were seeing before. And so as you can see in the equation down here, what we see is that this is the exact same thing as what we saw in the previous slide, but we have 2 different parameters that are actually added in, the alpha and the beta. So alpha and beta in general actually adds to 1, and depending on how you want to penalize this, the false negative and false positive, you're going to have to weigh that differently. So as an example, if we want to, for example, penalize false negatives more, we would have a higher number for your alpha than it would be for your beta. So if we set alpha to be 0.7, your beta would be 0.3. And so this allows us, as I said before, to focus on harder cases with low probabilities, because what we end up doing is putting this Tversky index into a focal Tversky loss so that you can focus on the harder cases. And what I mean by harder cases is, in the case of class imbalance, right? We talked about how there might be small tumors that may look like a dot on a page. And so for these things, what focal Tversky loss is that it focuses a lot more on these small, harder, these small tumors that are a lot harder to predict or with lower probabilities of actually being a tumor. They put a lot more emphasis, a lot more attention into that as a result of the case of class imbalance to kind of address that issue. So as you can see in this graph here, as the focal Tversky loss, when gamma is actually greater than 1, it becomes a lot more useful, because you see this like loss being increasingly a lot more, it's decreasing a lot more, as you can see in this graph. So it's super interesting in the way that we're able to use focal Tversky loss to focus a lot more on smaller tumors in the case of class imbalances. Another kind of method that we use is boundary-based losses for class imbalance issues as well. So what this actually aims to do is to minimize that distance between the actual ground truth and the predicted segmentation. So if we had to tie this back into dice loss, where you're looking at the mask of your ground truth as well as your predicted segmentation and that overlap, the boundary-based loss kind of takes that to another level by specifically looking not only at the distance, but also looking at how you're able to kind of minimize that distance as well. And so in the case of the images that you see here, what you'll notice is your delta G is going to be your ground truth versus your delta S is going to be that segmented mask or the predicted segmentation. And what boundary-based loss is aiming to do is to kind of using the surface areas and using all these like 3D images that you're kind of looking at to minimize that distance and the loss that you're actually predicting from the actual ground truth. So let's finish this entire thing off with federated learning. We've talked about the different solutions that are being used to address the first and the second challenge, I would say mostly, that we're actually currently facing. And now let's go on to a little bit more about federated learning and how this can address the third issue that we're facing, which is data privacy issues as well as access to more diverse data sets. So first of all, what is federated learning? As an overview, I love to kind of explain it through this image, which is mostly you have a central server for federated learning. And the central server has that model that exists there, right? As you can see, is like the black one. And you have these local kind of areas. So you have like the node here, and you also have the node on like the far right side. And think of these as, for example, your house or your phones specifically. They only store the data set that you're given. So a lot of these are private data sets or private data that you don't really want other people to see, such as photos on your phone or such as the belongings that you have in your house. And so what you have with this model is that you use this model to train on the different private data sets that you have on your local machines. So let's take the case of, for example, photos on your phone. What you want to do is to have a really good model that can predict faces, so facial recognition. And so every single person is going to have a very different data set of photos on their phones, right? They want to predict their moms, their dads, their siblings, their best friends, all these different things. And so this model is going to learn to predict all these different people that they kind of see in these images across like the thousands of photos that these people may have on their phones. So person A and person B would have very different people, right? And so what they do is that they have this model that trains it on that local data on the device. And through that training, it's going to have, or it's going to spit out results of that trained model. So specifically what worked well, what didn't work well, what wasn't it able to predict, what did it fail in. So all these outcomes that you can get from this trained model is basically sent back to that central server. So one key information to remember is that this information, like the data, is not sent back. It's only the information that was learned from that trained model will be sent back. And by collecting that information from trained model 1 to trained model 2, it's basically collected together and put back into that original central server model to come up with a new model that is more updated, that hopefully can be used again as a central server to be distributed to be learned more. So what I actually like to think of this in terms of, I guess, people and customer discoveries is think of it as like co-founders. For example, you, another person, you had 3 co-founders on your team. And 3 of these co-founders had to go out and do their customer discovery interviews, right? So what does their product specifically fit for who? So maybe this type of piece of clothing is more fitting for example, younger people, or maybe for middle age, or maybe for older people. This color. So all these different things you kind of collect. And your central server or your model is the type of questions that you should be asking your customers, as well as how you should be approaching these customers. So what you'll come to realize is that all these different co-founders are going to go out and do their customer discovery interviews using this model, right? And then as they come back, they learn something new. For example, person A might tell you, hey, I've learned that approaching younger people, you should kind of approach them with some sort of like happiness, enthusiasm, so that they're more willing to talk to you. And you kind of need to drop in some information that gets them to engage with you. So that's what person A finds out and learns. And they're like, this makes your customer discovery interviews a lot more engaging. You can get a lot more information from it. And then person B comes back and tells you, hey, one thing that I've learned about old people is that if you approach them with too much enthusiasm, what you actually end up getting is rejection. Because they're like, well, you look like fraud. You look like someone who only wants my money. So I don't really want to talk to you. So they seem a lot less approachable in those cases. So all of these learned information that you're seeing from these different co-founders are basically accumulated. They're combined like the trained model information that you see with the blue and the red. They're combined and they're aggregated back into that original central server and back into that original model. You kind of update that model. So now that we've learned that we shouldn't approach old people with enthusiasm and we should approach young people with enthusiasm, we create this new model, we update it. We're like, this is what we should be doing when we're approaching these different kinds of people. And we use that new model to redo our customer discovery interviews again. So this is basically, this iterative process is what federated learning is. And it's basically what has been being used in technology nowadays. So we'll see that in a next example where we have this entire new kind of day-to-day example where federated learning is used. So just before we get to that, I'm going to describe or give you a formal summary, in my opinion, of what federated learning is. It is a decentralized form of machine learning. So we kind of train a centralized machine learning model on decentralized data, as we were seeing before. So let's see this in an everyday example, as Google has showed us. So you know how we text on our phones, right? Every single time we text, there's always this like new, they come up with these kind of suggested words or suggested corrections. And so all of these suggested corrections are very much based on our texting habits. And so what federated learning does is that with all these like different texts that you're saying, this is basically how we think, right? So you don't want this data kind of shared to other people, or you don't want to share it to some sort of centralized way of learning. And so what happens is that you have these models that are trained on our phones, and every single time it trains and it learns these new things, that information is basically sent to that centralized system where that model is updated with the new updates or new learnings that it has from the local devices or the individual local devices. And it gets sent back to that centralized system where the original model is basically updated to something that's newer, so that as it's distributed to newer phones, it may potentially learn these texting habits a lot faster, because maybe out of 1 million people, 999,000 people actually use this exact same habit or have this exact same habit. So it's able to kind of implement that directly, immediately within maybe like a week or maybe a day of using the phone. So if we had to apply this to medical imaging, how does it solve that data privacy issue we were talking about before? And as you can see here, what ends up happening is this exact same thing as the phone situation that we're seeing. Each of the phones are now hospitals, where for each of these hospitals that we're seeing, you have their patient data, the medical imaging that you see in each of these hospitals. And what you end up seeing is that you kind of train those models, that central original model that we had before that's distributed to each of these hospitals, and you learn it. Maybe tumors kind of look like this. Maybe tumors look like that. What kinds of tumors can this model not predict out, even though it actually is? You have all these different information updates that are basically local updates that are sent back to the cloud into the original centralized system, where it can actually collect all this data and update that original model so that we can redistribute that to the local hospitals to relearn again. And hopefully with time, what we hope to learn is that you have this personal healthcare kind of system where now these models are able to really collect millions or billions of data set, learn off of those data sets, and be able to come up with a much, much, much higher and better and more accurate situation specifically for each patient based on, for example, their patient data. It's no longer just based on, for example, a doctor's personal own opinion on their own experiences, but potentially thousands and millions of doctors and their opinions all collected together to train this model so that we can come up with a better accuracy and much better prediction for each of these patients. So I would say the advantages for implementing federated learning into improving these, I guess, like segmentation models is that it makes it a lot more personalized, as I was saying at the end of the day, because federated learning can allow you, for example, in a texting situation, what you're able to do is to kind of recreate that person's habit and make it more tailored to that person's habit, just like how these segmentation models can actually become a lot more fitting to a lot of these other doctors. Another thing is that it preserves privacy. So it enables us to kind of bypass that privacy issue that we were talking about before. And obviously, last but not least, it allows us to access heterogeneous data. And what I mean by that is data from across the country, across different continents, where we're able to access data with people from different demographics, different lifestyles, different kinds of medical histories. All these different things will hopefully enable us to be able to train this model to an extent where our predictions and our accuracies are going to be a lot higher than what it used to be. Because at the end of the day, I'm going to repeat this once again, our models are only as good as the data that we actually feed it. So if we're able to gain access to a lot more heterogeneous data, hopefully this model is going to be a lot better at predicting abnormalities. So if we had to summarize everything, I would say there are a few things to kind of really keep in mind as we are going over these segmentation models. I would say there are a lot of limitations, and this basically includes the nature of tumors and medicine. It's so unpredictable, it's very uncertain. It's probably one of the most uncertain fields, to be honest, kind of like, think of it as like a stock market. So there are a lot of different things, abnormalities that kind of exist, and we kind of have to think about that as we're creating these segmentation models. Many of these tumors are going to look different. So what kinds of features, what kinds of characteristics should we be studying and really training on in order for us to have the highest level of accuracy and prediction? Other things include the nature of our understandings of computers. So how do these computers actually read these images? How are they interpreting it? What can they actually see? For example, for doctors, they have years and years of, I guess, like interactions, communications, and experiences with patients and even other doctors that enable them to be able to really have a good understanding of whether or not the small dot is going to be a tumor. Whereas for computer, they don't have those years of intuition. All they have is the intuition that we feed them. And so that's super important when we're thinking about it, because they can't predict the way that doctors can. So how can we get them to the level that doctors are actually able to predict tumors? How are we able to get them to the level of 100 or maybe even 1,000 different doctors predicting whether or not this is a tumor? Other things include privacy issues, as I was talking before, as well as data issues. For example, is our data clean? Are there any problems or issues with the labeling? Are there any issues with the type of data that we're using? And when we're considering the privacy issues, we really need to consider data privacy issues. I think this is one of the greatest things that we need to take into consideration as we're building these image segmentation models. Because right now, federated learning, in my opinion, has probably one of the best potentials in allowing us to bypass this to create a better model for everyone to use. And hopefully, as we challenge or as we attack each of these challenges one by one and be able to mitigate each of these issues, we're finally going to be able to come up with an image segmentation model that is going to be able to be implemented and validated across different data sets, different hospitals, to be able to help physicians and doctors and help them more efficiently diagnose these patients as we decrease their workload. So, thank you.